Well, that's all fine and well, and I think we feel probably pretty good about that. So let's extend into a word problem, okay? And remember, do not be afraid of these. You can do these. You have the skills to do these. We just have the added step of setting up the equation, then solving it. So we'll do some interpreting here, and we will solve this together. So Gardner is planting a rectangular garden area in a community garden. His garden will be next to an existing 12-foot fence. The gardener has a total of 44 feet of fencing to build the other 3 sides of his garden. How long will the garden be if the width is 12 feet? Now, while I am a horrible artist, and many of you saw that on the first day of class, I think pictures make word problems so much easier. If you have the ability to draw a picture, please do so. Okay, it will help you in the process, even if you're a terrible artist like me. So I'm going to start by just reading it again, and I'm going to draw a picture. So we have a gardener planting a rectangular garden area in a community garden. So we're in a community garden. If you don't know what a community garden is, it's a broad gardening space where multiple people can garden. So our gardener is planting a specific rectangular garden. So I'm going to draw a rectangle here in the community garden. So our garden is somewhere in the community garden. My garden will be next to a 12-foot fence. So it's right up along a 12-foot fence. And actually what we see is the gardener has a total of 44 feet of fencing to build the other 3 sides of my garden. So my garden's next to a 12-foot fence. And because it's butting up against this 12-foot fence, I actually only need to build fencing for 3 sides. So again, I'm going to use a different color here. What we can imagine is here is my 12-foot fence. Okay, that's someone else's fence. We're in this community garden. Maybe that's the end of their garden, and they said, hey, why double the resources? Just use my fence as a cutoff for your garden and my garden. Okay, so this is maybe his name's Jim. This is Jim's 12-foot fence. And we are building a rectangular garden, and thanks to our friend Jim, we already have 1 side of the fence. We have a total, let's keep going here, of 44 feet of fencing to build the other 3 sides. So while we know this fence is 12 feet, the other 3 black sides we only have 44 feet of fencing. That's how much material we have. So maybe I'll draw a little 3/4 circle or oval here. Okay, that black fence, that's made up of my 44 feet. Can't be bigger than 44 feet. Okay? How long will the garden be? How long will the garden be if the width is 12 feet? Okay, so we're thinking about rectangles here. And what we know about rectangles is rectangles have width and they have length. And they're telling me the width is 12 feet. Now, where does this apply to our picture? Well, we already know that one side here is a 12-foot fence. And what we know about rectangles is opposite sides are congruent. They're the exact same. So we would say this is also 12 feet, and we're calling that the width. Calling that the width. Okay, so we'll put a W there. Maybe it's better if I put it on the inside. Calling that the width. Well, the other side of the rectangle then is the length. The other side of the rectangle is the length. And we don't know the length. That's what we're trying to find. How long will the garden have to be? We don't know how long the garden is. Okay, we're figuring it out as we go along. Okay? So how are we going to solve this? Well, we kind of have a visual. I think this is where the visual is super helpful. We're focusing here on our 3 sides. Okay? On our 3 sides. And we know the 3 sides cannot exceed 44 feet of fencing. So I'm actually the first part of my equation is going to be 44. Any chance I get in a word problem, I tend to look for a total. I try to see if what is one side of the equation that this all is equaling. And what I can see here is I'm trying to find the length of the sides of the garden, and I know I can't use more than 44 feet of fencing. Okay? Well, what is that 44 feet being made up by? Well, it's being made up by 3 sides. We've got 1, 2, and 3 sides making up that 44 feet. Let's be specific. We know one of these is a length that we don't know, plus the width, which is 12 feet, plus another length. Okay? We're using 44 feet of fencing to build 3 sides. 2 of them we've called the length, and we don't know what they are. One of them is 12 feet long because it is the width. Okay? Again, you might be thinking, rectangular garden, shouldn't we have 4 sides? Well, remember, our neighbor already covered the one side with 12 feet of fencing. So you can see through the visual here in the various colors how I arrived at setting up my equation. If you're sitting there going, man, that is confusing. I don't really understand what you did there. Put a star by it. If you're like, I don't know if I could do it in my own, but I kind of get where you're coming from, that's a decent spot to be. And if you're sitting there going, yeah, I could have done that on my own, good, you're in a really good place. So take a moment, figure out where you are specifically, and then make a note of it in your notes. If you're more in the, I'm not really getting this, email me. Let me know that you're struggling with this word problem. Okay, so let me rewrite this so that we can maybe not with all the crazy colors going on. So now that we have an equation set up to model the situation that we're observing, let's go ahead and solve it. Our goal is to find the length. Well, how do we find a variable we don't know? Well, what we're going to do is we're going to try and get that variable by itself. So I notice that I have a couple L's and they're already on the right side. So I'm certainly not going to try and move the variables to the left side. So I'm going to try and get the variable all by itself on the left side or the right side. And then the constants and everything can go on the left. Well, if the variables are going to be on the right side, the 12 has no business being here. So if we do 44 minus 12, we get 32. Again, of course, if we subtract 12 from the right side, that will cancel out with the positive 12. And we're just left with L plus L. Now, L plus L, we haven't talked a ton about this situation here, but hopefully you know how to simplify this. We have 2 L's here. They are exactly alike, so we can combine them because they are like terms. Similarly, if I have an apple on my one part of my desk and an apple on another part of my desk, you don't go apple, apple, you go 2 apples. Okay, so combine your like terms here. I have 2 L's here. We can rewrite L plus L as 2L. And now what we're going to do is we're going to divide both sides by 2 to get L by itself. 32 divided by 2 is 16. And what we see here is we have a length of 16. Okay, and you go, great, I did it with some help. I solved the word problem. Not quite yet. Remember, we always want to check our work. You go, how am I going to check my work here? Well, see if your answer makes sense, right? We had 44 feet of fencing. We have the width as 12 feet. Therefore, the length we're saying is 16 feet. Let's see if that makes sense. How do I know if it makes sense? Well, if I only have 44 feet of fencing, and the length is being made up twice, plug 16 back in. See if indeed, when we have a length of 16, if this meets the specs we're looking for. Well, 16 plus 12 is 38, or 28, excuse me. And 28 plus 16 is 44. Hey, we have that true math statement we always look for when we check our work. So we can confirm that given the specifications we were given, 44 feet of fencing with a width of 12, we want a length of 16 feet. Okay, so that's again, hopefully you see here when it comes to the equation process, nothing is new. We just had the added step of setting up our picture and setting up a picture and then an equation and then solving the problem. Okay, so we want to solve for B here. That's our goal. We're trying to solve for B. And what we are trying to do, obviously, is we want to get B by itself. But we see something here that we haven't really necessarily seen before. Okay, something a little bit new. What we notice is that I have these parentheses. You know, typically what we're doing is we're automatically jumping into, okay, where does the variable go? Does the variable sit on where do I want it to be on the left side? And how can I get it by itself? Let's move the constant. Let's divide or multiply depending on what's attached to the variable, what type of coefficient, and go from there. But here we have these parentheses, okay? And unlike in the past where we've seen negative 2b minus 4 equals 12, what we see here is that negative 2 is not only applied to the b, but it's also applied to the minus 4. Okay? We have negative 2 times the b and the minus 4. That's why the b minus 4 is in parentheses. So before we do anything else, and hopefully you've seen this in your past math classes, what we're going to have to do is we're going to have to distribute that minus 2. Because the minus 2 is multiplied by both the b and the minus 4, what that means is we need to distribute it to both. So before we do anything else, handle our parentheses, okay? Because otherwise we can't move anything. We can't cancel out anything right off the bat. So we go ahead and distribute the negative 2. And I get negative 2b. And then negative 2 times minus 4 will be positive 8. Remember, negative times a negative equals a positive. And that equals 12. And we haven't done anything with the right side yet. We just distributed. We didn't do any inverse operations or anything like that. And by distributing that negative 2, now we see an equation that we saw actually way back in 2.2. One that we know how to solve. First, what we're going to do to make lives easier on ourselves, we're going to move the constant. What do I mean by that? I mean, we want to get the variable alone, so we need to remove this positive 8. How do we remove the positive 8? Well, we subtract 8 from the left side. That will cancel out with the positive 8. And we also subtract 8 from the right side. On the left side, that leaves me with negative 2b. And on the right side, I am left with 4. 12 minus 8 is 4. From there, I go, how is the negative 2 related to the b? Well, the negative 2 is being multiplied by the b. That inverse operation would be division. So we will divide both sides by negative 2. Negative 2 divided by negative 2 is just 1. 1 times b is just itself. So I have b on the left side. And on the right side, 4 divided by negative 2 is negative 2. Okay? And I'll box my answer. Actually, wait, I'm not going to box my answer yet. I know better. What I'm going to do is I'm going to check my work. Okay? I'm going to plug in negative 2 in for b to ensure that it produces a true mathematical statement, a true equation. Well, I get a couple different ways I could solve this. I could distribute the negative 2, but since I have like terms within the parentheses, I can just go ahead and combine them. Negative 2 minus 4 is negative 6. And then, of course, I have negative 2 times negative 6, which is 12. 12 equals 12 is a true mathematical statement. Therefore, b equals -2 is a solution for my equation. Okay, let's do one more example. 2x divided by 3 plus x over 2 equals 7. 2x over 3 plus x over 2 equals 7. And we're sitting here and we go, okay, I see how I have two like terms on the left side. I've got both my variables over there. So I want to get those variables by itself. And, both those fractions have x's. But I don't really know how to combine them. What do we do in this case? How do we solve these types of problems with fractions? Well, your goal is going to remain the same. You're going to want to get the variable by itself. And again, both of these have x's, so they are like terms. So how can I combine them? Well, I want you to think back to middle school math. What do I do when I have 2/3 plus 1/2? Let's remove the x's for a second. Let's not think about them. If you just had these fractions, what would you do? Well, I hope if you jog your memory, what you would say is, well, to add fractions, I have to have like denominators. How do we get like denominators when we have two fractions that don't have the same denominator? Well, we identify a common denominator. So I look here, I've got 3 and I've got 2. What would be a good common denominator? Well, I would do 6. So I'm going to change both of these fractions to have a denominator of 6. But I'm not going to fundamentally change them, because what I'm going to do is I'm going to multiply them by the exact same thing on top and bottom. So if I look at 2/3 here, I want to have a denominator of 6. How am I going to get that denominator of 6? Well, I need to multiply the denominator by 2. 2 times 3 gives me 6. But to not fundamentally change the fraction, I will multiply by the same thing on the top. Again, the logic there mathematically is 2 over 2 is just 1. 1 times 2/3 is just 2/3. So I haven't fundamentally changed the fraction. I've just changed how it looks. 2/3 and 4/6 are the exact same thing. Do the same thing for your 1/2 here. I want the denominator to be 6, so I need to multiply the denominator by 3. I will do the same to the numerator, and I get 1/2 is 3 over 6. So I've changed how the fractions looked, but I haven't fundamentally changed their value. And now, because I have like terms, I could add the fractions together. Well, believe it or not, we're going to do the same thing up here. It's just a little different because we have x's. When you look at our original problem, I have 2x over 3 plus x over 2. If it makes it a little easier on your eyes, recognize that on the top here, we just have 2 times x happening. So this can be rewritten as 2/3 x plus 1/2 x. They're the same exact thing, right? If you envision x as a number, we can rewrite 2x over 3 as 2/3 x. Again, because the 2 and the x are multiplied together, they mean the same thing, okay? Maybe this helps you because then you look at this and you go, oh, hey, we just saw this. Now I just have an x involved, okay? So what am I going to do? Well, I'm going to transition the fractions to have like denominators. Just as we did in our example. And now I can combine my like terms. They are like terms because they both have an x and they have the same denominator. So what do we do when we have like terms that have the same denominator? We're adding them, we add the numerators. So what these will combine to be is 7 over 6 x, and that equals 7. That equals 7. Well, again, a little bit more complex because we had to do some denominator transition, or we had to rewrite our fractions. So, but in any case, we got to our place where we've combined our like terms. And again, my ultimate goal is to get x by itself. So what do I need to do here? Well, the 7/6 is being multiplied by the x, so I divide by 7/6 using my inverse operations. I have to do that to both sides. Well, 7/6 over 7/6, anything over itself is just 1. So the left side, I will just have x. And on the right side, I have to do 7 divided by 7 over 6. But we know when we divide fractions, we just multiply by the reciprocal. Instead of dividing by 7/6, I multiply by 6/7. I get 42 over 7, which is equal to 6. So I find here that x equals 6. X equals 6. And again, if I wanted to check that, plug it back in for x way up here. So what I would have is I would have 2 times 6 divided by 3 plus 6 divided by 2. And that should equal 7. 2 times 6 is 12. So I have 12 divided by 3 plus 6 divided by 2. 12 divided by 3 is 4. 6 divided by 2 is 3. And I have two sides that are equal, meaning my solution is correct. Okay? Again, we got more and more complex as we went through this video, but hopefully you are seeing the same patterns. Our ultimate goal is not changed. Isolate the variable by using inverse operations. Now we're adding in different layers like some distributive property and combining like terms, but the ultimate goal is still the same. Now, if you're a process person, if you like order, if you're like, I like to know what I need to do when to solve these problems, here's what I would recommend. Here's what I would recommend you would do. Here to this point in this process, hopefully as you've seen, gets added to a little bit by bit as we go through this. Hopefully you see that as these problems get more complicated, the process gets a little more complicated. But again, here's what I would recommend. As you saw in the last problem, if you have any fractions that occurring, make sure they all have common denominators. It's going to make it easier to combine like terms. Okay, so make sure your fractions all have common denominators. That'll make life a lot simpler for you as you solve these. Make sure also we go ahead and use that distributive property to get rid of any parentheses. Again, we can't start canceling things out until all parentheses are removed. We got to make sure we distribute what we need to. We also then, at that point, combine any like terms, whether you've had to distribute, whether you had to rewrite some fractions. Go ahead and combine any like terms that are on the same side together. And then from there, once you do steps 1 through 3, you should be looking at an equation that looks a lot like 2.2. And from there, you're just isolating the variable using inverse operations. Okay, so hopefully that process helps. Hopefully this makes sense. Again, if you are confused, let me know, star your notes, and let me know how I can help.